Okay, let's begin this discussion with the idea of formula weights. In the last chapter, we talked about average atomic masses. And now, and by the way, I'm using mass and weight interchangeably, even though the two aren't the same. But here on Earth, we can use them interchangeably. Grams are, in fact, a unit of mass. But we know the average atomic mass of each element in the periodic table. If we want to know the mass of a molecule or compound, which, as you know, is a combination of those, then we're going to add together the average atomic masses of the species. So if we take fluorine is one of the diatomic molecules. Remember, they're hydrogen, nitrogen, oxygen, and all the halogens. So let's calculate the molecular weight of fluorine. You've got 2 fluorine atoms times 19.0 atomic mass units per fluorine atom, and that gives us 38 AMU. So the mass of the molar mass or molecular weight of fluorine is 38 atomic mass units per fluorine molecule. All right. Let's look at another example. This time let's look at ammonium sulfate. Ammonium sulfate, you'll remember, consists of the ammonium ion, which is NH4+. That's the one polyatomic cation that you're responsible for. And sulfate, SO4 2-. That's one of the many polyatomic anions that you're responsible for. Since ammonium has a +1 charge and sulfate has a -2 charge, the formula for ammonium sulfate is NH4 2SO4. So to calculate its formula weight, now notice here there are 2 nitrogen atoms, 8 hydrogen atoms, 1 sulfur, and 4 oxygens. So it's going to be 2 times 14.0 AMU plus 8 times 1.01 AMU plus 1 times 32 AMU plus 4 times 16 AMU. And that turns out to be 132 atomic mass units. So the mass of a compound or molecule is just the sum of the masses of the atoms that make it up. All right, let's look at reciprocals and see from that if we can get to one of the key concepts in chemistry, and that is the relationship between the count, which is what we are most interested in, and the mass, which we can measure very effectively in the laboratory. To do that, let's look at this idea of reciprocals a little more carefully. So copper has a density of 8.96 grams per cc, which means that if you have a cc or a milliliter of copper, its mass will be 8.96 grams. But we can also say something else. We can say that 8.96 grams over 1 cc is equal to 1 cc over 8.96 grams. After all, both relay the same piece of information, and that is that if you have a cc of copper, it weighs 8.96 grams. In other words, the ratio is equal to 1. But if you do the math out, this becomes 0.11 cc's per gram. So that same piece of information can be used 2 ways. It can tell us what volume a certain mass has, or it can tell us what mass a certain volume has. Okay, well, let's look at another example. Suppose we have a piece of filter paper that weighs 1/10 of a gram, and so we can write 0.1 grams per piece. Well, we also can write the reciprocal just as we did here and say that there is 1 piece over 0.1 grams. But if you do that math out, that's 10 pieces per gram. And this gets at what we're trying to do. We can weigh the filter paper and then use this relationship to relate the weight or the mass to the number of pieces of filter paper we have. So if you had a whole handful of filter paper, a whole pile of filter paper, instead of counting out the individual pieces, you could just weigh the whole pile and multiply by 10 pieces per gram, as long as each piece weighed 1/10 of a gram. We're going from weighing to counting, or from counting to weighing, which is what a major piece of this course is all about. So let's look at this in an example involving atoms and molecules. We know that an atomic mass unit is about the mass of a proton or a neutron, very close to the mass of a proton or a neutron, and it turns out that that's 1.66 times 10 to the minus 24 grams. So the mass of a nucleon, proton or neutron, is 1.66 times 10 to the minus 24 grams, in the same way that the mass of our filter paper was 0.1 grams. And we can apply the same approach. We can say 1.66 times 10 to the minus 24 grams per nucleon, or 1 nucleon over 1.66 times 10 to the minus 24 grams. Well, if you do that math, that turns out to be 6.02 times 10 to the 23rd nucleons per gram. 6.02 times 10 to the 23rd is the number of nuclear particles, protons or neutrons, that we need to have the mass register as 1 gram. So hydrogen atoms, for example, H11, has 1 proton and an electron whose mass is too small to worry about. So what this means is that since hydrogen atoms contain 1 nucleon, 6.02 times 10 to the 23rd hydrogen atoms are contained in a gram of hydrogen. So we define a mole as 6.02 times 10 to the 23rd things. Can be nucleons, can be donuts, can be carbon atoms. It's a number, like a dozen is a number. So if we recall that an AMU is exactly 1.66 times 10 to the minus 24 grams, and there are 12 nuclear particles, 6 protons and 6 neutrons in a carbon-12 nucleus, then we can say the following about the number of carbon atoms in 12 grams. In 12 grams of carbon-12, at 1 nucleon, for every 1.66 times 10 to the minus 24 grams. This relationship now tells me how many nucleons there are in 12 grams, but 1 carbon-12 contains 12 nucleons. And when you do that math, it turns out that there are 6.02 times 10 to the 23rd carbon-12 atoms in 12 grams of carbon. So there are 6.02 times 10 to the 23rd hydrogen atoms in 1 gram and 6.02 times 10 to the 23rd carbon atoms in 12 grams.